So we have the question 1 here. The figure represents the waveform of a sound wave. The wave is traveling at a constant speed. So it says that the wave is traveling at one speed, right? So speed is connected with two other factors in a formula. V equals F lambda frequency into the wavelength. So here the graph given here shows you a transverse wave. But remember, sound is not a transverse wave. As a waveform to learn, to get into calculations, theories and all, we use this graph. But sound is a longitudinal wave. Remember that. Sound is a longitudinal wave. Alright. So, displacement of the particles are given upwards and downwards. The arrowheads are given. And some of the other arrowheads are also marked over there. The question asks you here, label with the letter X the marked distance corresponding to the amplitude of the wave. So what is called amplitude? Amplitude is the maximum displacement of the particle. How much the particle moves, right? In a vibration during a wave motion. So here you can see the wave is given with almost 2.25 waves, actually 2.25, not two and a half of half actually, right? I mean half of the half, right? 1/4. So you see here, when you come for this is the maximum displacement shown. The question asks you to label it as X. So I'm going to mark it X here. So X is the maximum displacement of the particle, and that is what the amplitude is. And then the question says, label with the letter Y the marked distance corresponding to the wavelength of the wave. So, Y, the marked distance corresponding to the wavelength. What do you mean by the wavelength? When you come for a wave, right? This is completely one wavelength. It's one complete wave. So, the length of this wave is what we term as the wavelength. So, we can take it between 2 points which are next to each other, having the same state, having the same phase. And this is a starting point of one wave, this is a starting point of the other wave. So I can continue the wave like this, starting. So you can take it between the two starting points, or else, in fact, you can take it. So let me take it again in the same flow. Or else you can take it between the two consecutive crests. There is also wavelength, two consecutive troughs, also the wavelength. So next to each other two particles here is also the wavelength. So wavelengths could be given in three different ways. So the question asks you to label it according to the diagrams given. You can see the first part here at this point. It is actually a half of the wave. And when you come for the second part here, the second arrowhead, it actually shows you more than one wave it is showing. And the third arrowhead down there here, it shows you from half of the midpoint of one wave to the midpoint of another wave. Can you see? If you're going to start from here, almost if it is a wave, it should have one complete vibration. A complete vibration refers to 4 steps are there. There are 4 steps. What are the 4 steps here? Starting from this point, 1, 2, 3, 4. How many steps are there? 1, 2, 3, 4. 4 steps are there. You can see 4 steps are completed at this point. This is the arrowhead. So it is the arrowhead showing you the wavelength. So there we have to mark it as Y. We have to mark it as the point Y here. So accordingly, those two questions I have done. All right. So you see, the next point is asking you, state what happens to the amplitude and the wavelength of the waves if the loudness of the sound is increased at constant pitch. So I want you to do this like, you have to draw the diagram first. Put the question number 1, take it as waves question paper, write revision questions. Question paper 4, and draw this diagram, please. You don't want to write the questions, just the question number, and then mark the answers, write the answers on your writing book. Okay. But the diagram you have to draw, otherwise we can't mark that X and Y. Draw the diagram and then label it. Make it fast. Then take the question number 1 and 2. It's already marked, I think. Okay. Now you can go to the question 2. State what happens to the amplitude and the wavelength of the wave if the loudness of the sound is increased at constant pitch. Constant. What happens to the amplitude and the wavelength of the wave? What is happening to the amplitude when the loudness of the sound is increased? Now we learn pitch is directly proportional with frequency. You increase the frequency, pitch increases. You decrease the frequency, pitch decreases. Right? Loudness is directly proportional to the amplitude. When the loudness is increased, that means the amplitude has increased. Okay? Loudness decreases, amplitude decreases. Amplitude decreases. And the pitch is constant. If the pitch is constant, frequency should be constant. Frequency should be constant. Right? If the pitch is constant, frequency must be constant. Keeping the same constant frequency. Okay? Keeping the same constant frequency. The sound is moving. The question asks you when the amplitude is increased, loudness is increasing, when amplitude is increasing, right? What will be happening to the wavelength? Nothing changes in the wavelength. Nothing changes in the wavelength. Why is that nothing changes in the wavelength? Because as I told you now, okay, frequency is same. Frequency is same, right? That is the idea. Something like this. Like at this point, I'm taking this graph. Let's say on the same thing, keeping the frequency same, amplitude is increasing. What do you mean by the frequency same, amplitude increasing? Something like this. Frequency is same. There is no change in the frequency. Can you see that? The frequency is same. I have taken just an example as a graph, not the same graph on the tube. Okay. So you can see the amplitude has increased. Frequency is not changed. Why do I take the frequency is not changed? Because the pitch remains the same. Pitch remains the same means there is no change in the frequency. So according to V is equal to F lambda, if frequency is constant, right? Frequency is constant and the sound speed also the same. Sound speed also the same. Nothing changes in wavelength if these two are same. If these two are same, nothing changes in the wavelength. So let's say speed has increased, then we can say the wavelength will be increased. Or speed has decreased, wavelength is decreased, we can say. But nothing changed like that. So we have to say amplitude, it is increasing. Amplitude is increasing when the loudness is increased and wavelength stays the same. Wavelength stays the same. So take the question 2-1, question 2 and question number 1. Okay. 2, 1. Right there, we have two lines for amplitude and wavelength. One is for amplitude, the other one is for wavelength. Take it like that. Amplitude increases as the loudness is increased. Amplitude increases as the loudness is increased. The second line, wavelength stays the same. Wavelength stays the same. That is only answer. I'm giving you the reference also. Wavelength stays the same as both the speed and the frequencies are constant. As both the speed and the frequency are constant. Are constant. Okay. Right? There you can draw this diagram as an example. Put it as an example. Mark the red color ones up here for your reference. Right. Look at the next question there now. What does the next question says? The pitch of the sound is increased at constant loudness. The pitch is increased. If the pitch is increased, frequency increases. Okay, frequency increases. And the question says that the sound wave is at a constant speed that is given at the very first line. Speed is same. Okay, for the next part, speed is same. Speed is constant, right? And pitch is increased. If the pitch is increased, frequency increases. So according to V is equal to F into lambda, this person is constant. And these two when you are taking, okay, when the frequency is increased, what should be happening? Wavelength must be decreased. To keep this person constant, to keep this person, the wave speed to be kept constant, F and lambda should be 1 over relationship. That means inversely proportional. Frequency you increase, wavelength decreases if you want to keep the speed constant. If you want to keep the speed constant, when you increase the frequency, wavelength decreases. When you decrease the frequency, wavelength increases. Wavelength increases. So that is how it changes. It changes. So this is inversely proportional. Inversely proportional. Okay. So wavelength decreases. And the question says, what about the amplitude? Now, constant loudness is given, right? If the loudness is constant, there is no change in amplitude. So, how do we write the answer? Question 2. Question 2. There. It's asking me the amplitude. Sorry. Write the amplitude there. A stays the same as the loudness is constant. A stays the same as the loudness is constant. A stays the same as the loudness is constant. As the loudness is constant. A stays the same as the loudness is constant. Amplitude, A means amplitude. For wavelength right there, wavelength reduces. Wavelength reduces. Why is that wavelength reducing? Wavelength reduces as the frequency is increased at a constant speed. At a constant speed. Fine. What is the next question says there? Second question is B. Okay, I mean the first question B, sorry. A ship uses pulses of sound to measure the depth of the sea beneath the ship. Sound pulse is transmitted into the sea and the echo from the seabed is received after 54 meters, 54 milliseconds, right? The speed of sound in seawater is 1500 meters per second. Calculate the depth of the sea beneath the ship. So how do we find out the depth of the sea? How to find out the depth of the sea? Now, it is actually the distance, right? Speed is equal to, right? Distance over time. Speed is equal to distance over time. So how do we find out the distance then? How do you find out the distance? Distance is equal to speed into time, right? Distance is equal to speed into time. And the speed is given 1500 meters per second into the time is given as 54 milliseconds, and the question says that transmitted into the sea and the echo from the seabed is received. So it goes down and comes back again. It goes down to the oceanic bed, the seabed, and then it comes back again. So that means two paths are there. So when you use that particular time, you are not finding out the depth, double of the depth you are finding out. Why? From the sea it goes down and comes back again. So two paths. So what are we supposed to do? This time we have to reduce, we have to divide by 2. So I'm writing 54 milliseconds, right? Milli means 10 to the power minus 3. Milli I have to convert into seconds. Milliseconds I have to convert into seconds. 10 to the power minus 3 because milli means 10 to the power minus 3. And dividing by 2. So get me the answer in this way. And before converting, we have to check out with the question. If you want to really find out the depth in meters or milli, any other units given. Okay, but here straight away it is meters. So we have to definitely convert that into the standard. Give me the answer. How much does it gives you? 1,500 into 54 dividing by 2. 40,500 into 10 to the power minus 3. That means almost 40.5 meters. 40.5 meters. So that is the gap here. That is the depth here. 40.5 meters. Got it? Fine. So like this, I want you to do the next question now. First question I have done with you. Okay. Go to the next question, please. The second question goes up with again the sound wave, the frequency, the physical quantities are what mainly connected. Put the question number, use the correct formula. The formulas are already done. Okay, use the correct formula and give me the answer. And the third question also you have to do. And for the third question, you have to draw a rough diagram. You have to draw a rough diagram. You have to take, if you have a graph paper, draw it accordingly, or take a rough diagram and sketch it on, and then find out the answer. Yes, you have to sketch that because the question asks you to draw the normal and all. Do the second and the third question both quickly. I'm giving you about 10 minutes time. All right. 10 minutes time I'm giving you. Quickly do it. So you have the paper, you can go with that.
Sir, sir, what's the topic?
Wow, this has you came now, right? This is actually you're doing a paper. I think you received the paper in WhatsApp. Could you please check it? First question was done.
No.
Second question I gave time. Get the paper, please. Sharon, have you done? Could you do it? Question two. We'll take the question two. I hope the question two you should have done completely. Check with your answers. So this as you can go ahead with this question today. Question 2A. A sound wave in air consists of alternate compressions and rarefactions along its path. So I told you earlier, can you remember? Transverse waves, right? Transverse waves. Okay, third question. Okay, good, right. Here. So the transverse waves, they make crest and troughs, while the longitudinal waves make compressions and rarefactions, and in fact, sound is a longitudinal wave. Right. Explain how a compression differs from a rarefaction. How is this compression differs from rarefaction? How do you give the answer for this? When you come for compressions, these are the compressed areas. The particles are coming closer. Rarefaction, particles are getting away. Again, getting closer, getting away. So, when you consider these areas, the compressed areas, the particular density would be high. The particular density would be high than the particular density in this rarefactions. So the question asks you explain how a compression differs from a rarefaction. 1 mark question. 1 mark question. So how do we give the answer there? We can write there here in this way. Compression is a region. You can write the answer making the question number 2, and it is A1. Question number 2, A1. Compression is a region where the air particles are closer, where the particles, you can say where the particles are closer, and thus it gives a high pressure. Why? Particles closer together means particles when they are closer together, pressure given by those particles would be high. A greater pressure would be given. Okay, so that is compression. Rarefaction, particles are away from each other, relatively the pressure would be less. Okay, is a region where the particles are closer and thus the pressure is higher. Pressure is higher. Right. Number 2. Explain in terms of compressions what is meant by the wavelength, the frequency. Now, wavelength already I have shown you there. When you come for a transverse wave, the length between two consecutive points next to each other points, okay, points having the same state, having the same phase, right? When you're gonna consider this level, okay, let's say this is the wave motion. You can take next to each other two crests, or next to each other two troughs, or starting to starting point of another wave. All these are wavelength, and this comes on a transverse. But how do we define that on a longitudinal? One compression to the other compression. One compression to the other. Let me start from midpoint of this, midpoint to the next. Or the midpoint of the longitudinal to the midpoint. Or starting to starting, ending to ending. So anyhow, between two compressions or between two rarefactions, what is the length? This is called the wavelength of a longitudinal wave. So explain in terms of compressions what is meant by the wavelength of the sound. So let's write there. The length between two compressions. I don't use the word rarefactions here because the question says in terms of compressions. Can you see that? In terms of compression. So I don't want to say rarefactions. It doesn't mean rarefaction is wrong. Rare fractions also you can take, but here you can't take since the question says terms of compressions. Okay. So the length between two successive or two consecutive compressions. Number two, the frequency of the sound. So frequency means that is the number of waves passing per second or number of oscillations happening per second. So in a compression, how do we say that? Number of compressions passing per second one particular point. So if you consider one particular point, you are moving, you are letting the wave to move on. You mark this point, the waves pass, the waves keep passing, let's say. The waves keep passing this point. You have to check for 1 second how many waves are passing this particular mark, particular level. So how many waves are passing, that is called frequency. And how do you find out the waves? How many compressions? So number of compressions passing for a point. Now, how do we exactly take that compression as collectively for one wave? Because one wave contains only one compression. Between two compressions, right? Between two compression means one compression and one rarefaction is there. Okay. One crest and one trough is there in a transverse, likewise. Okay, or half of that and half of this, likewise, it would be there. So here I can say how many compressions are passing per second a point. This is called the frequency. Or else I can say how many compressions are released out, emitted out per second. Because what is the compressions emitted out? That is what passing out. Okay. So let's write there the question 2. Question 2A, Roman number 2. Number of compressions passing a point for a unit time. Number of compressions passing a point for a unit time. Number of compressions passing a point for a unit time. Okay. Look at the next question now. At night, the bats emit pulses of sound to detect obstacles and prey. The speed of sound in air is 340 meters per second. A bat emits a pulse of sound of wavelength 0.0085 meters. Calculate the frequency of the sound. So how do we find out the frequency now? B is equal to F into lambda, right? So the frequency should be equal to V by lambda. You have to subject. V equals F lambda. That is the formula you have learned related to this. F equals V over lambda. What is V here? How much is V given? 340 meters per second. 340 meters per second. Dividing by how much is the wavelength given there? Wavelength is 0.0085 meters. 0.0085 meters is the wavelength given. Give me the answer now. It should be 340 dividing by 0.0085. How much is it? It gives you 40,000, right? 40,000. 40,000 hertz, or else you can write it as 40,000 kilohertz. But it depends on the question's unit. If the unit is given as kilohertz, then you have to write 40. 40 kilo. Kilo means 10 to the power 3, right? Okay. Here nothing mentions. The unit is not given, right? Check if the unit is given. Yeah. The unit is not given, so you can keep the answer as either 40,000 hertz or 40 kilohertz. 40 kilohertz. State why this sound cannot be heard by human beings. Why can't we hear this sound? That's because of our audible range of sound is 20 hertz to 20,000 hertz. 20 hertz to 20,000 hertz. We can't hear a sound less than 20 or more than 20,000. We can't hear the sound less than 20 or more than 20,000. That is why 40,000, which is more than 20,000, we can't hear. So let's write the answer there. The question series it's asking you, subjecting you, oh man, just common human beings. Yeah. The audible range of man is 20 hertz to 20,000 hertz only. So 40,000 cannot be heard. So 40,000 cannot be heard as it is above the upper threshold or upper level. As it is above the upper threshold, upper level. Right. The pulse of sound hits a stationary object and is reflected back to the bell. It goes, hits on the surface and comes back. So two paths. Like the same earlier the ship. Okay, one question we did now, right? In the first one. So it goes, it hits on the surface, comes back, right? Two paths. The pulse is received by the bat 0.12 seconds after it was emitted. So it goes and comes back after 0.12 seconds. Calculate the distance. How do we find out the distance now? Distance equal speed into time. Speed into time. What is the speed given? Already the speed was given 340 meters per second. And the time is given 0.12. 0.12 we have to divide by 2. Why am I dividing by 2? Because it goes down and comes back. Okay? Or else let me take on a horizontal path. It goes and comes back. So two paths are there, but I need only one distance, no two distance. So it's moving on like this, right? And it's coming back. Okay, so it's moving for two distances. I need only one distance. So I'm dividing the time by 2. So how much should it be? Check. But the answer is 340 into 0.12. 0.0. Is it 20.4? 20.4 meters. 20.4 meters. Wait. Oh, sorry. One thing we missed. Question says calculate the distance traveled by the pulse of sound during this time. You see, one mistake we did. What is that? During this time means, guys, we don't want to divide by 2. Am I correct? Correct it, please. Correct it, please. We don't want to divide by 2. Why? Because the question says during this time, complete distance. Complete distance shall be 40.8 then. 20.4 we got earlier. That should be doubled up. 40.8 meters. So please correct it. 40.8 meters. 40.8 meters. Right. Please to complete the question 3 quickly. Take the question 3 quickly. And this is, Shan, I think you have already started. This is, make sure you draw the diagram roughly and then mark it down.
Okay, sir.
They're showing an object O placed in front of a plane mirror M. Plane mirror M. So this is the plane mirror actually. This is the mirror. So this is the shaded side. So here the waves coming on. And this is the object O. Object O is what given here. And the two rays from the object to the mirror. The mirror are shown. For one of the rays shown, draw the normal to the mirror. Mark the angle of incidence. Label this angle X. You can do it. It's a very easy question. Nothing hard. Quickly do it. Do it quickly.
Sir, after doing this, should we like send a picture?
Sorry? Pardon, please.
So after doing this, should we like send a picture?
No, no need, no need. Because it's just a diagram where we have to label the parts, okay? So we can discuss it. But you have to show me. Show me over the screen, okay? Fine. So look at the questions accordingly now. Draw the normal to the mirror for one ray, one of the part. You have to draw the normal. Mark the angle of incidence. Label this angle as x. And then the reflected rays for both incident rays. Both the incident rays, you have to mark the reflected rays. Construction lines to locate the image of O. Label this image I. Right. Construction lines to locate the image of O. Now, we learned about the correct method as well as short method as well. Short method as well, right? Now, first, let me take the normal. Let's say I have taken here. Normal should be straightly perpendicular. Perpendicular, you have to mark the normal. In fact, here also you can do the same thing. Here also you can do the same thing, the normal. Normal. And the question says, you have to label it as what? X, right? No, just draw. Draw the normal. You don't want to draw both. I'm showing you both the points, right? You can choose one of them. So you are drawing the normal, but the normal should be exactly 90 degree. Okay, 90 degree means you don't want to measure it. You can use a ruler to draw it and then you can mark it, right? 90. And then the question says that mark the angle of incidence, label this angle as x. Now, what do you mean by the angle of incidence? Angle of incidence is the angle between the normal and the incident ray. So this is the incident ray, right? Incident ray and the normal. And you have to label this angle as x. So this gonna be the incident angle. And if you take here, this shall be the incident angle. Don't mark both. One of the angle you can mark. Okay, one of the angle you can label. And then question says that into the reflected rays for both the incident rays. You have to draw the reflected rays. So make sure when you draw the reflected rays, your image should be on the same line somewhere. Your image should be on the same line. You have to make sure your image shall be on the same line. So let me just draw it. It is not must for you to draw like this. I'm just pointing out the path. Okay. Then it has to be on. Now I have to take the rays on. I have to take the rays. This has to be moving away, and this also has to be moving away. This also have to be moving away. Now you see, both of them are moving away. Both of them are moving away each other. Probably they are moving away each other. Something like this. Can you see? Angle I'm going to make somewhere equal. The equal angle I'm taking. Okay. An equal angle I'm going to take. So it goes somewhere like this. Right? So the opposite side I have to drag. And this also I have to take the equal angle. I have to take an equal angle somewhere the equal. So you can see it's also moving away. Also moving away. So these are the two reflected rays. Reflected rays. These are not refracted, reflected rays. And then construction lines to locate the image of O. Image of O. So how do we find out the image of O now? How do we find out the image? Real rays. Okay, real rays are not meeting up. As the real rays are not meeting up, what are you supposed to do? Okay. Right? What are you supposed to do? Both the sides you have to drag it. Both the sides you have to drag it. When you drag it, you know what happens? Let's say, probably I have to correct something. I think so, because yes, I have to. So for because it should be on the same line. Can you see? Has to be on the same line here. Why do I take that? Because what is the object distance? Can you remember the short method? What is the object distance should be the same image distance as it is a mirror. So when I keep the point here, definitely this point should be the image. This should be the image point. So marking the image point, I'm going to draw this. I'm going to draw this. So I have to do a small change on my ray diagram here. You see accordingly. You have to definitely use the rulers. Okay. So you can see now this is my reflected. Correct? Is that clear? So this is how we are supposed to do. Right? So this is the point where the image is made. This is the point where the image is made. And you can see they are on the same line. Same line. Did you understand that point? This is why we have to use the pencil, you know. If you use a pen, you can't erase like this, right? You have to use a pencil, even on the answer sheet. Using your short methods, you can find out the answers. Okay. So could you please show me your diagrams? Turn on your cam, please. Sharon, please show the diagrams. Yes. This is you
So I
can.
used a pen.
Sorry, you have sent it.
I used a pen.
Okay, that's fine. Show me the diagram, please. Just show it. I just want to see what you have drawn. Yeah. Sharon, turn on, turn on. Turn on the camera and show me the diagram. Oh yeah, let's see this as. Okay. Yes. So you see, the last one is what wrong. Others are correct, right? The last one gone wrong because you couldn't correct it with the pen. So please make sure we are using the pencil. We are using the pencil. Right. Sharin, so correct the diagram, please. Sharin. Yes. Slightly up. Oh yeah. Wait. Wait. Hold on. Fine. So the last one, there's a small mistake with it. You know what? Can you see here? This ray, you have taken something like this. This part. You have taken crossing in this way. Can you see that? You have taken crossing like this, right? This, right? It is crossing out, correct? That's the wrong thing, right? Should be connected at the point where it is falling on the mirror. This is the point where it is falling on the mirror, right? From this point only, you have to take the reflected ray. This is wrong. Okay. Do correct it, please. Yeah. Okay. Fine. And the next question. B. Circular wavefronts from a point from a point source in a tank of water strike a straight barrier. The barrier is given there. Okay. The reflected wavefront seem to come from a single point. Reflected wavefronts, reflected ones, seem to come from a single point. Single point. Mark a dot to show the position of the point and label this point as C. What do you think? Where should it be? This is how it is given, right? Okay. It's somewhere here. Correct. Yes. You got the diagram, right? Question asked you. The reflected wavefront seem to come from a single point. So these are the incident waves, right? Incident wavefronts are what moving one. And all of them are meeting at this point. Can you see? All of them are moving towards and they are meeting at this point. Slightly out. Straight away from the center. We'll take off. This is the point all of them are meeting. And the question asks you, the reflected wavefront seem to come from a single point. This is the point. Okay. And draw a mark to show the position of this point and label this. Label this. Okay. How do you label that? Mark a dot. You mark a dot here and label it as C. Label it as C. Right? Draw the diagram, please. And we don't take it down because the barrier is there here. This is our barrier. Okay, this is the barrier. Draw as accurately as you can the reflected circular wavefronts. Reflected circular wavefronts should be going on like this way, right? That is from here, it should be moving out. And it would also be moving out as the circular arcs, the circular wavefronts. So minimum 2 circular arcs you have to mark. You have to mark. Each joining the correct points. Right?
Sir,
Yes.
so that means this point should be exactly in the middle of the barrier line.
Yeah, that we take in this way because it's circular, right? All of them are moving from one point here, right? From this point, from the center of this circular point only, all the waves are moving. And all of them are hitting on a circle, on a barrier, exactly on a horizontal path. Can you see the image given there? The image shows you like a barrier like this. It is not in an angle, correct? It's not in any angle. It's not in any angle. It is a horizontal barrier. So we assume that it should be exactly from this point. And moreover, you can see 1, 2, 3, all 3 wavefronts are meeting. I mean, on one line, you can meet up here on this axis. And others are not there. If you take them also, would be the same on line. So that is the line joining up over there, right? And from that line only, we have to take the wavefronts out. So the wave hitting one would be moving out like this. And you have to take the same wavefront. The same wavefront means almost almost in this way. Don't make the same space. Why same space? Because there is no change happening. There is no diffraction happening over there with any other points. So should be the same. Should be the same space. To show the same space only, I am taking that closer. You can see both sides. Minimum 3 you have to mark. Minimum 2. Minimum 2 you have to mark. So the next one also you can take it like this. I can take it closer. Okay. So they are the reflected wavefront. So how do I take that? Why am I taking closer to them? Because the wavefronts, the wavelength is there. The wavefront's length is there here. This is the wavelength. The wavelength should be the same because there is no change happening in the frequency of speed. Because the same medium, right? It is not moving into another medium. It is not moving into another denser bottom. Same medium is coming back. So there is no change in the speed. Speed not change, and the frequency also same. Wavelength won't be changing. You have to show the same wavelengths there. Please draw it accordingly. Minimum 2 you have to draw there. Right. Look at the next question now. Question 4. We'll do it together. A police car. Question is done, right? Oh, wait. Yes. A police car siren emits sound waves that vary in pitch. Vary in pitch. Pitch is changing means you have to understand who is changing. Frequency is changing. The pitch changes, frequency changes. The pitch changes, frequency changes. Tick 2 boxes that apply to the sound waves emitted by the siren. Tick 2 boxes that apply to the sound waves emitted by the siren. A police car siren emits sound waves that vary in pitch. Tick 2 boxes that apply to the sound waves emitted by the siren. Right? So, what are the sound waves? What are the boxes you have to take that apply to the sound wave? It is not electromagnetic, correct? You don't want to write all, you have to take the question 4A, you have to write the correct answers only. Electromagnetic you can't take because sound waves fall under mechanical, it needs a material medium. Longitudinal, it's true, it is a longitudinal wave because sound is not transverse, it is longitudinal. Transverse you can't take, visible you can't take, frequency 0.1 to 10 hertz also you can't take because less than 20 hertz we termed as infrasound, more than 20,000 hertz we termed as ultrasound. So the sound that is audible for us is between 20 hertz to 20,000 hertz. So frequency 100 to 10,000 we can take because 100 to 10,000 is not our audible range, but it is within our audible range, isn't it? 100 to 10,000, it is within our audible range, right? So you can take that answer, you can take because it is applied. It doesn't mean, it doesn't say here audible range is 100 to 10,000, okay? It says just the frequency. So the frequency, so 1 to 10 means 2, 3, 4, 5, all of the numbers are belonging to that, right? So likewise, okay? Frequency 100,000, okay, but 1 million, okay? 1 million you can't take because up to 20,000 only it is. So we can't take the last one, only those two. The second one and the sixth one we have to take, second and the sixth one, okay? And then the question says, figure 7.1 is a top wave of one wavefront, top wave of one wavefront of a water wave before it strikes a hard boundary, right? The direction of travel of water wavefront is given. Name the process that occurs as the wavefront strikes the boundary. What is the process? What we learned now. It may be a circular wavefront or a straight wavefront. If it hits on a barrier, a completely closed barrier, it comes back again. This is called reflection. Reflection. So what is happening here? Reflection. So question B1, name the process reflection. Explain in terms of the wave theory what occurs as the wavefront strikes the boundary. When the wavefront is striking the boundary, what would be happening? Okay. So now, once it hits on, it won't stop, right? It forms another wave. And that the wave would be moving into the opposite direction. I mean, opposite direction means it comes back. It comes back. And there is no change in the speed, right? Because the medium has not been changed. The same water. So same water, same medium, same density is there. As it is coming back to the same medium, there is no change in the speed. No change in the speed, and the frequency is also not changed. And that is why even here we took same speed, same frequency, and the wavelength gonna be same. So it moves back, giving the same wavelength. And now this is about circular, right? And here the question is about straight. So the straight wavefront hitting on would be coming out, making an equal angle of reflection. Angle of incidence and the angle of reflection would be equal, giving that the ray moves out. Ray moves out. So even the wavefronts are making the same angle. Wavefronts are making the same angle with the boundary. So how do we get it on? We have to explain that. Let me show you with the diagram. So there's a point, right? Right. So you see, this is the part. Okay. This has to come back out. How would it be coming out? Making an equal angle. Right? Making an equal angle, it comes out. So when it is hitting on the surface, here the normal is, you see, this is a normal. So making an equal angle here. Making an equal angle here. You can see there, right? Making an equal angle here. It goes out. It goes out. So what I was supposed to say, it hits on the barrier, forming a new wavefront, it comes out. Having the same medium, frequency will be same, wavefront would be, the wave speed will be same, having the same wavefront. The wavefront means when you are drawing the rays, let's say you are going to draw the wavefront here, this is the ray, right? This is the light ray, okay? This is the light ray. So this is the wavefront, let's say. You have taken the wavefronts in this way. So, can you see here? The wavefront is going to be the same space. Wavefronts will be having the same space between them, because there is no change in the wavefront. There is no change in the wavelength. Okay. If the question asks you to draw it, this is how we have to. This is how we have to draw. Okay. Fine. So you see accordingly. Let's write the question there. The answer there. Explain in terms of wave theory that occurs as the wavefront strike the boundary. Striking on the boundary, right there. Striking on the boundary. A new wave is formed and reflects back to the same medium, and reflects back, and reflects back. A new wave is formed and reflects back. The wave has the same speed. The wave has the same speed and the same frequency. The wave has the same speed and same frequency. The wave has the same speed and the same frequency. Only 2 marks given, right? Yeah. The angle of reflection of the ray, the angle of reflection of the reflected ray is equal to angle of incidence. Is equal to angle of incidence. Angle of incidence. That's one. 2 points and up here, 3 points. All right, next question. State whether there is an increase, a decrease, or no change in the wavelength of the wave after it strikes the boundary. We already spoke about that. There is no wavelength change. Why? Speed same, frequency same. So there is no change in the wavelength. So we have to say no change. That's all. Because 1 mark question, no change in the wavelength. No change in the wavelength. No change in the wavelength. The speed of the wave is 3 meters per second and its wavelength is 7 centimeters. Calculate the frequency. So now the question is very common. How do you find out the frequency? V equals F lambda, F equals V over lambda. So the frequency wavelength is given, the speed is given 3 meters per second. Dividing by the wavelength is 7 centimeters. Centimeters means I have to take it as minus 2 meters. 10 to the power minus 2 meters, right? 7 centimeters, right? I have to take it as 7.0 into 10 to the power minus 2 meters. Minus 2 meters. So 3 dividing by 7. It gives you 0.428. 428 into 10 to the power minus 2. 0.428 into 10 to the power minus 2.
So can't you just put in decimals?
Yes, we can.
Normal decimals.
Yeah, we can convert.
42.8.
How do we convert that? It gives you almost you mean this one, right? Yeah, we can. 0.07. 0.07 and 10 to the power minus 2 when you come up, it becomes 10 to the power plus 2. That means this gives us 42.8. I can write it as 43 hertz. You can keep it as 0.07 as well. Same thing. Right? Minus 2 when you take up becomes plus 2. So 42.8, that means 43 hertz. I can give the answer as. Fine. So again, next question too. The last one there. During a thunderstorm, the thunder and lightning are produced at the same time. At the same time, same bolt, both of them are produced. But light comes first and then only the sound comes. A person in some distance away from the storm. Explain why the person sees the lightning before hearing the thunder. What is the reason? Lightning, the light travels faster than sound in air. Light travels faster than sound in air because light travels at a speed of 3 times 10 to the power 8 meters per second, while the sound travels somewhere around 330 meters per second. 330 meters per second. So let's write there. Light travels faster than sound, much faster than sound. Light travels much faster than sound, much faster than sound. A scientist in a laboratory made the following measurements during a thunderstorm. Time from start of storm and a time between seeing the lightning and hearing the thunder. That means a gap between when you see the light and when you hear the sound. How many minutes after the storm started did it reach its closest point to the laboratory? How do you find it? How many minutes after the storm started did it reach its closest point to the laboratory? What is the closest point to the laboratory? Time from start is given. Check. Time between seeing light and hearing the thunder. How do we find it out? Now, the light I see and the sound comes there, right? The gap between that is very less in 1.6. Can you see that? 3.6, 2.4, 1.6. Okay. 1.6 minutes, right? 1.6 seconds, right? That means within 1.6 seconds, if someone is coming faster, what do you mean by that? The speed is high. So it should be closer. The thing is, speed is high means actually speed is same here, right? Should be short time when you are coming means speed should be high. But here the light has the same speed. So the same speed means distance should be less. Distance should be less. That is the idea. Is that clear? Okay. So now distance equal V into T. V equals distance over T. Distance over T. So now V is same. When the time drops down, time is less, distance should be less. That is the idea. Correct? When the time is less, distance should be less as far as the V is same. And why am I saying it is same? Because light, you consider wherever the light is, light has the same speed. The moving light has as a wave, it has the same speed. Right? So who has the lowest time to reach the point? You are at the laboratory. You see the light and you hear the sound. Between that, the gap is 1.6. Okay. Why? Sound is traveling like that, no? No. From one point it is produced and it reaches to your ears after 1.6 seconds means that is the time it is reaching from the point produced to your ears, and that is the distance it has traveled. So lower the time, lower the distance is. I hope you understand that point. Okay, lower the time, lower the distance is. So accordingly, 1.6 should be the gap between. But the question asks you, how many minutes after the storm started did it reach its closest point? The closest point is where it is moving 1.6 seconds. And the time should be time for start. Storm started, right? 4 minutes. Time should be 4 minutes. So the answer B1 should be 4 minutes. You understand that? Question asks you not the gap. For that gap to happen, what is the time the storm start? Okay. 4 minutes. 4 minutes. How can you tell that the storm was never immediately over the lagoon? How can you say that? Yes. What does the question ask you? Read and tell me. How can you tell that the storm was never immediately over the lagoon? Throughout this, you can see there is no zero timing, right? Why? No zero timing means, okay, if it is immediately above means within not even a second it comes. Why? For 1 second it travels 3 into 10 to the power 8 meters per second, right? Okay. So if it is immediately above the laboratory means, okay, it won't take even a second. Then the gap between the lightning and the sound hearing, the thundering should be zero. It cannot be zero, even less than that it should be. But if it is second only seconds, right? Okay. So it cannot be there because no timing given like that. No timing given like that. All of them are giving a non-zero difference. Okay. All of them are giving a measurable time difference here. So there is no difference given which cannot be measured. Like suddenly, let's say if it is immediately above your head, you see the light, you hear the sound. At the same moment, why? Both of them are reaching. Both of them are reaching very quickly because sound is anyhow moving at the same speed. Light speed is very high, right? And it travels that within a very short time. Okay, within a very short time. The same distance. Okay, so let's write there. The table shows always a measurable time difference. A measurable time difference where there is no zero gap. Where there is no zero gap. Right. When the storm started, it was immediately above a village 1200 meters from the laboratory. 1200 meters from the laboratory. Using the information and the information from figure 7.1, calculate the speed of sound. How do you find out the speed of sound now? 1200 meters away from the laboratory. That means if it is producing the sound and the light 1200 meters away, right? That is the distance it should be traveling, right? And you have to check if there is a time related to given. So the laboratory is there here. The village is 1200 meters away. The village here is 1200 meters away. And just check out with that gap. If something is showing there, right? Time from start of storm minutes. Storm in minutes. How do you take that? Whom you have to take? The time between seeing lightning and hearing thunder. How to find it? It's just 1200 meters. The question asks you to find out who? Question asks you to find out the speed of sound. Speed of sound. How do you take that?
So by measuring those measuring instruments.
Measuring? Now can you see there? The question says that like this, no? Time from start of storm is 0. Right? Time from the start of storm. The question says that when the storm started, it was immediately above the village. Okay. It was immediately above the village. That means the storm started should be the 0 timing, right? Isn't it? Immediately above the village means should be the 0 time, correct? 0 time. So timing should be 0. And the time between seeing the lightning and hearing the thunder, how much is it giving at the 0 timing? That means the starting of storm is 0 timing, right? Starting of the storm is 0. 0 minutes. Time from start of storm. Okay. Time from start of storm is 0 minutes. Why? Because it is immediately above. Immediately above. So 0. Time between seeing lightning and hearing for that 0 is 3.6, right? Okay. So 3.6 seconds will be taken to see the light. To observe to hear the sound after seeing the light. Now the person they are here see the lights and the sound comes after 3.6 seconds. After 3.6 seconds, that is the idea. You understand that point? After 3.6 seconds only it is coming. So how do you find out the speed now? Speed equal distance over time. Distance is 1200 meters divided by what is the time taken? 3.6. 3.6 divided 6. You understand that point? 3.6. It gives you somewhere about 333.33 meters per second. This is the usual speed of time, speed of sound. State the assumption you made when you calculate. What is the assumption we are making? I told you it is immediately above. It is at the ground level. We are assuming that it is the lightning occurs at the ground level, immediately above. Immediately above. So that we can take that 3.6 seconds here. Otherwise, if it is above, somewhere above the village level means it's very hard because that calculation should be also added to find it out. And moreover, we assume that there is no wind because if there is wind, the sound to come, it takes time. Takes time because sound needs a medium, but light doesn't need a medium. Even if there is strong wind or what wind, light doesn't need the medium. Light travels in the space, but the sound needs the medium. What medium they are in the air? Air medium. So if air is blowing, in the opposite direction, let's say, if the air is blowing to the opposite direction of the sound, then the sound takes some more time to reach the point. So then it affects our timing. So sometimes the question may ask you like this. Theoretically, this is the answer you are getting, but practically at a time on a day, it is not receiving at this time. Or it is not giving the same on a calculation. Why is that? Then you can say that is because of maybe there is a strong wind in the opposite direction of the sound motion, the sound wave motion. That is why it is delayed. So here we assume there is no sound, there is no strong wind or no wind in the opposite direction. So two assumptions we can make. So let's write down. We assume that there is no wind. We assume that there is no wind. Right, the next point. Assuming that assuming that the lightning occurs at the ground level. Assuming that the lightning occurs at the ground level. Assuming that the lightning occurs at the ground level. Lightning occurs at the ground level. Lightning occurs at the ground level. Okay. Right. What about the next one? Some waves are longitudinal, some waves are transverse. Some waves are electromagnetic, some waves are mechanical. Right? Put ticks in the below table to which of these descriptions apply to the light waves and the sound waves. Light waves, is it longitudinal or sound waves? Light waves, is it longitudinal or transverse? It is transverse. Okay, transverse. So light waves, you have to take it in front of transverse because all electromagnetic waves are transverse. They don't require material medium and they move as transverse, forming crest and troughs. So crest and troughs means they are transverse. So light waves should be transverse and electromagnetic. Sound waves, they are longitudinal. They make compressions and refractions. The three questions we did like the same. And they are mechanical. They need a material medium to propagate. So draw the table and take them properly. Draw the table and take them properly. So hope you understood these theories. We did some questions in order to revise as we are done with the lessons. Okay. So force and motion we are done. Electricity we are done. Waves we are done. Waves we are done with the questions too. Okay.